Hi, so welcome to MathStat 341. This is lecture 24. And what we're going to do today is we're going to talk about some proofs of the central limit theorem, at least in a special case. For tossing a fair coin, as a nice exercise, you can try to see, can you make the argument work if the coin is not fair? We will then, generalize this, and what we're really doing is we're really discussing a very simple random walk, where you move left or right equally with probability 1/2. If anybody is interested in research problems related to this, I'm happy to talk about that. We will then segue into generating functions, which is one of my favorite methods in mathematics. This is one of the reasons why I love teaching probability, because so many of the things I truly love just show up here. We've seen Fibonacci numbers before, and we've seen Benet's formula, where you can jump to whatever Fibonacci number you want. It's incredible when you have something like that. And the main idea of generating functions is you take local data and you put it together and you make this global object. And then you just pray that you can say something about that global object. And if you can then often use that to deduce things about the inputs. So it seems like some kind of strange magic at first. You put in something that you don't really understand, you get a new object, which you do understand, and then somehow you can use that to deduce things about the original objects. We'll then apply this as time permits to Poissonment random variables. Poissonment random variables just happen to be a really nice distribution that's easy to work with, and they occur in a lot of good places. So for the general items, we're going to see the power of Stirling's formula. And we talked about the main term, which isn't too bad to get. And then there's different types of analysis you can do for the error terms. If you do a little bit more work in the integral test, you can actually get the error term without too much trouble. We will talk about building intuition through special cases. This is what we're going to be doing by tossing a fair coin. You have to be careful, though, because sometimes your intuition can mislead you, that you could be looking at a case that's so special that it doesn't really talk about what's going on in the general case, and you could be misled. So always be careful about that. And then the last, and this is one of the reasons why I love generating functions so much, is it is easy to be overwhelmed in algebra. How do you find a good path through it? How do you find a way to approach the calculations and not just get lost? How do you find what would be a good next step to try? And so as much as possible, we want to automate that process. This is very similar to the quadratic formula. If I give you a quadratic, it should not be hard for you to solve it. You may not be jumping for joy at trying to put the stuff in and evaluate it, but it's a very mechanical procedure. And so we want things like that, which is a bit mechanical, so we know, okay, this is going to work. If you remember your series tests from multivariable calculus or real analysis, you have the ratio test and the root test, where you just go through and you just calculate this ratio or this root, and that tells you whether or not it converges. It's very mechanical. The comparison test is beautiful and wonderful to use, but you have to have that flash of intuition. What should I compare it to? Interestingly, the ratio and the root tests are actually just comparison tests with geometric series. That's what's lurking under the hood. It's just the algorithm does that for you. All right. So just review. We'll see these slides very often. They're from the book that I wrote, and I get money every time they use. It's the way the copyright works. So normal distribution, 1 over square root of 2 pi sigma squared, e to the negative x minus mu squared over 2 sigma squared. And then the central limit theorem is, if you just sum a bunch of independent, identically distributed random variables, then their sum converges to being normally distributed. Which normal? Well, it depends how you sum them. Do you subtract off the mean and do you divide by the standard deviation? Do you look at the average? So depending on which one you look at, you can get a different normal. Doesn't really make that much of a difference. In terms of comparisons, we often like to use the standardized. We often talk about the z-score, because now it's the standard normal and we just need one table. Now, in the 21st century, when you have access to so many different things, not a big deal. We are going to use Stirling's formula a lot. So gamma of s is the generalization of the factorial function, and n factorial is approximately n to the n, e to the minus n squared of 2 pi n. And we saw why this is true last time, at least as a consequence of the central limit theorem, which was a really nice application of CLT. We saw a little bit where the e came from by looking at n plus 1 factorial over n factorial, and we could see the e emerging. So we saw that this was reasonable. Okay. I didn't put in the images last time. I had to add them. So this time I actually put them in beforehand. Here is semi-efficient Mathematica code to just quickly look at some binomial distributions. And I'm just counting how many heads there are if I toss a fair coin n times. I did 10, 30, 50, and 100. And if you look at it, it does look like it is becoming normally distributed. And it does look like the mean is growing. And, wow, that really looks like the mean is exactly equal to the number of tosses that we are doing divided by 2, half the number of tosses. Okay, so definitely by 50, this is looking pretty normal. Even by 30, that's looking fairly normal. Again, in a math or stats class, you don't want to use the word look, but you want to be able to quantify this and get to the chi-squared, your goodness of fit tests, later in the semester. All right, so here is the random variables we're going to study. We're going to toss a fair coin, and with probability 1, we get a head, and we'll record that as a +1. And with probability 1/2, we get a tail, and we will record that as a -1. And otherwise, the probability will be 0. So again, normally you do head or not head. Head is 1, tail is 0. Why am I doing 1 and -1? As opposed to 1 and 0. Yes.
So that your mean is 0.
Yeah, my mean is now 0. So I don't have the process mean is not growing. I have things centered. And so now if I look at the sum of the x's, this is going to tell me the excess of heads over tails. Why do you think I'm choosing to toss 2 n coins rather than n coins? What must be true if I toss an odd number of coins? What are the possible values? Yes, if I toss an odd number of coins, I'm either going to end up with ±1, ±3, ±5. If I do an even, I'm going to be 0, ±2, ±4. I'm just centering things nicely. Really doesn't make that much of a difference. But, again, anything I can do to try to make the algebra a little bit nicer, I will do. Okay? What is the expected value of S2n? Its expected value is just sum of the expected values, and the sum of the expected values is 0. And now what about the variance? The variance of the sum is the sum of the variances because they're independent, right? But we have to be careful because these are not the standard Bernoulli random variables. The standard Bernoulli takes on the values 0 and 1. This takes on the values -1 and 1. All right, so we just have to go through and actually do some calculations. The variance of xi is going to be 1/2, and then it's going to be 1 minus the mean squared, plus 1/2 -1 minus the mean squared. So what does that equal? I did it equals just 1. So the variance of S2n would just be 2n. Okay. So now we want to calculate what is the probability that S2n equals some value. So what are the possible values that S2n could equal? What kind of numbers could S2n be? Okay, integers. What kind of integers? Even integers. So I might as well just write the probability that S2n equals 2k. Because I know if I put in an odd number, the probability is just going to be 0. So I might as well just restrict myself to this. So how would I have this equaling 2k? This means we have n plus k heads and n minus k tails. Right? Because we have to have an excess of 2k heads. Every time we get a head, it's a +1. Every time we get a tail, it's -1. So that's exactly how I'm going to have exactly 2k for my sum. All right, so what I want to do is I want to figure out what is the probability that I have exactly n plus k heads. And we know S2n is a binomial random variable with probability 1/2 and 2n tosses. So we have an explicit formula. So this probability is just going to be 2n choose what? N plus k. And then for each head, it happens with probability 1/2 to the n plus k. And then each tail happens with probability 1/2. And now it should be apparent why I want to look at a fair coin. Because the 1/2 n plus k, the 1/2 n minus k is just going to be what? It's just 1/2 to the 2n, as coin is fair. Okay, so if we didn't have a fair coin, then unfortunately this part could change depending on what k is. And you would have to figure out how to deal with that. All right, so the probability that S2n equals 2k is 2n factorial over n plus k factorial n minus k factorial times 1 over 2 to the 2n. And we want to analyze this. What do you think would be useful to analyze this? So what do you think we should use to try to analyze all these factorials? Stirling's formula, right? Foreshadowing, right? There's a reason why that was on a slide or two ago. There's a reason why we spent a lecture talking about Stirling. Use Stirling's formula. Well, Stirling's formula is good when the quantities are large. Let's quickly think 2n factorial, that's going to be large. But what about n plus k and n minus k? Well, k could be negative. So let's think about it. We know the variance is equal to 2n, right? So the standard deviation is of size square root of 2n, right? So by Chebyshev, if you move a couple of standard deviations away, the probability becomes very small. So, the probability, we are, say, log n standard deviations from the mean is at most 1 over log n squared, which goes to 0. So Chebyshev is very, very weak. But it's just saying, look, if we are 10 standard deviations away, the probability of being 10 standard deviations away is at most 1 over 100. For something like normal or binomial, it's much less than 1 over 100. Let's take the number of standard deviations to be growing with n. And log n is not growing very rapidly. What this is saying is the probability that you're more than log n standard deviations away is 1 over log n squared, which is going to 0. So that means with probability approximately 1, we have 0 minus log n times the square root of n less than equal to 2k less than equal to 0 plus log n times the square root of, square root of 2, right? Then with high probability, the number of steps we have is not much larger than a little bit more than square root of n. This means that n plus k and n minus k are approximately n. So factorials are large. So it's going to be okay to use Stirling's formula, because the probability that 2k is a little bit more than square root of 2n away from 0 is so small, it doesn't really matter. So when I'm looking at n plus k factorial and n minus k factorial, I'm really not that concerned. So this is just justifying that we can use Stirling's formula, that we don't have to worry that we have something very small. Okay, so now we have the probability of S2n equals 2k was 2n factorial over n plus k factorial n minus k factorial 1 over 2 to the 2n, and n factorial is about n to the n e to the minus n square root of 2 pi n. And now it's just algebra. So everything that I'm doing here is in the book. I am just going through the algebra. And you can see why I really did not want to review this lecture. All right. So we have the 2n factorial. That's going to be 2n to the 2n. I'm going to write that as 2 to the 2n, n to the 2n, e to the minus 2n, square root of 2 pi times 2n. And then I divide by n plus k factorial and minus k factorial. So for the first one, I'm going to write this, I'll do it slowly, as n plus k to the n plus k, and I'll do n minus k to the n minus k. And I have an e to the negative n plus k and e to the negative n minus k. That's an e to the negative 2n. And I have a square root of 2 pi n plus k and a square root of 2 pi n minus k. And of course, I also have the 1 over 2 to the 2n. When you look at this, you can see a lot of things are beginning to cancel. The e's cancel, the 2 to the 2n cancels. We have an n plus k and an n minus k. Let's pull out an n from each of those factors. So if I pull out an n from each of those factors, how many n's do I pull out from their product? And which cancels with the n to the 2n upstairs. I've got a square root of 2 pi, which is going to cancel with 1 of the square root of 2 pi down below. So if I've done the algebra correctly, I should get 1 over square root of 2 pi. Then I would have the square root of 2n over the square root of n plus k n minus k. And then I would have 1 over, let me just write this. 1 plus k over n to the negative n minus, I'm sorry, n plus k. And then 1 minus k over n to the negative n minus k. Everybody agree with this? I've just pulled out the power of big N that cancels with the n to the 2n. And now I have 1 plus k over n. And it's supposed to be to the n plus k in the denominator. That's the same as just saying it's the negative n. Okay, now I'm going to look at what happens as n goes to infinity. As n goes to infinity, the square root of 2 will cancel that square root of 2. The square root of n over the square root of n minus k, do you agree that that's approximately 1? Because we know k is not that much more than 0. And so the first factor over here is looking like 1 over the square root of pi n, as n gets very, very large. And then the question becomes, how do I handle the rest? I'm sorry? Well, that's the thing is, does it go to 1? So note that 1 plus x over n to the n converges to e to the x, right? So if you're just a little bit away from 1, if you raise it to a fixed number of powers, you still stay very close to 1. But if I raise it to a variable number of powers, then that small little excess or deficiency can be magnified tremendously. So in the book, I go through some bullshit arguments. What if we just say, well, look, k is really small. So what if we try, the first goes to 1 plus k over n to the negative n, which should then be 1 over 1 plus k over n to the n, which would be e to the k, would be 1 over e to the k. The other one, 1 minus k over n to the negative n, would be like 1 over 1 minus k over n to the n would be 1 over e to the minus k. So the product is approximately 1. The problem with that is k does depend on n. K could be as large as square root of n. In fact, we expect k to be on the order of square root of n. That's the size of the fluctuations. And so if k is of size square root of n, when I have 1 plus k over n to the k, that could be significant. And so we have to be a little bit more careful. We could also play some other games. I could say, let's forget about the k's, and let's take this to the negative n, this to the negative n. If we multiply them together, we get 1 minus k squared over n squared to the n. Well, the n squared is so much larger. You know, this is really handwriting bullshit, right? And depending on what I want, I could probably say, yeah, you approximate this how you want, but this is not rigorous. So this is not a good approach. And so it's so bad, I'll use the multicolored. So I need a better way to approach problems like this. When you look at this, 1 plus k over n to the n plus k, this is a huge product, right? Who hears the voices in their head? What are the voices saying? You've got huge products. What should you do? Take the log. It should be instinctive. Whenever you see a product, take logarithms. That's the only way we can do this rigorously. So here is the lemma. The top just hasn't gone down there. So 1 plus k over n. Ooh, I'm not quite sure. Oh, I've got the 1/2. The 1/2s don't really matter. Converges basically to e to the k squared over n. And so let's look at this. Let's let p be 1 plus k over n to the n plus k, 1 minus k over n to the n minus k. So the log of p is n plus k log of 1 plus k over n plus n minus k log of 1 minus k over n. Now k is much less than n. K is around square root of n in terms of size. So that means k over n is really small. So we saw this function, log 1 plus k over n, I think in the first day of the semester. What problem were we looking at when we saw something like the log of 1 plus k over n? The birthday problem. We used Taylor series. The log of 1 minus x is approximately negative x. The log of 1 plus x is approximately x. The error term is going to be much smaller. And so the question is, how deep do we need to go? Is it enough to keep just the first term? Let's do the next term. For Taylor, it would be minus x squared over 2. And here I think it would be minus x squared over 2. So now let's start playing things out. So we have n plus k. The log of 1 plus k over n would be k over n minus 1/2 k squared over n squared plus big O k cubed over n cubed. So big O just means an error term of size k cubed over n cubed. K is a little bit more than square root of n. So k cubed over n cubed. K cubed is a little bit more than n to the 1.5. This is n cubed. So it's a little bit less than 1 over n to the 1.5. Even when I multiply by a big number like n times something like 1 over n to the 1.4 is going to go to 0. If I hadn't kept this term, k squared over n squared, k squared can be of size n. K squared over n squared could be of size 1 over n. When I multiply something by size of n, oh crap, that could be a main term. So I have to be careful. I have to keep that. Okay. So I'm just wondering if this is a typo. And then the next one is plus n minus k. And then I've got minus k over n, so it's going to be minus k over n minus 1/2 k squared over n squared plus order k cubed over n cubed. Okay. I think there is a typo in this one. I think I want to reciprocal. So we'll fix this in a moment. So is everybody comfortable with how we're getting these expansions? We're just taking the logs, and as we expand, we say, well, look, if I kept this term, it's going to be so small, it's going to look like a 1 over square root of n. It's not going to matter in the limit, because I know k can't get too large. And then the other terms are going to be even smaller. You can dominate it with a geometric series. So if you do a little bit more analysis, you can show that the sum of all the other terms won't contribute. Well, now let's look at what we have happen. We have a k over n and a negative k over n. So the n times this and the n times this, they cancel. Then we have a k squared over n. And we have, oh, a k squared over n. So we're going to get a 2k squared over n. I'm just doing it term by term. 2k squared over n. For the next one, we have n times negative 1/2 k squared over n times negative 1/2 k squared over n. They reinforce, and it's going to become negative k squared over n. Okay. Then the next one is I'll have negative 1/2 k cubed over n squared, and I'll have a plus 1/2 k cubed over n squared. Those cancel. So I'm going to just write plus damn small. Right? Everything else is going to be much, much smaller. Well, what's 2k squared over n minus k squared over n? This is basically k squared over n plus much smaller. Okay, nope, so there was no mistake. I did get it right. And so we see that the log of p looks like k squared over n.
I guess so for the order of k cubed over cubed, we're multiplying it by n.
Well, then it'd be k cubed over n squared. But k is a little bit more than square root.
Oh, okay.
So say k is even 1.6, say k is even 0.6.
Okay.
Then k cubed would be 1.8. And when you divide by n squared, that's n to the negative 0.2.
Yeah, I'll check for your notes.
Yep, and so that's enough to just show that because k is a little bit more than square root of n, it's not going to be enough to really contribute. And so what I did is I was just a little bit careful. I said, you know, let's go up to k is like 2n to the 1/2 plus epsilon. I was just being a little bit careful. And so this is the log of p, looks like k squared over n plus something small. So then that means p is going to be e to the k squared over n, e to the much smaller. And this is just where the big O, the error term of size n to the negative 1/6 comes from. It's just, you're just doing the bookkeeping to see just what is that really small stuff. All right, so we now know that this product, we had initially said it was approximately 1. That's a bad estimate. A better estimate is it's about e to the k squared over n. All right. Any questions on the algebra here? Okay, if you become a math professor, you can do this once a year. All right, so we show that the probability of S2n was 1 over square root of 2 pi times that product, but that product was in the denominator. So here, we would have to put in a negative sign. So it's going to be 1 over the square root of pi n times this. So the probability that S2n equals 2k would be 1 over square root of pi n, and it would be e to the negative k squared over n times e to the much smaller. Okay. And that much smaller, this tends to 1 as n goes to infinity. Goes to 1 as n goes to infinity. Does this look like a Gaussian? Yeah. Yeah, I mean, look, I've got a k squared. Now, we know that the expected value of S2n is 0, and the variance of S2n was equal to 2n, right? So if it's a Gaussian, which Gaussian should it be? It should be a normal with mean 0, variance 2n, or 1 over square root of 2 pi times 2n, right? Times e to the negative x squared over 2 times 2n. And so we are very close to that. Right? So what we now need to do is we need to play the algebra games. Now we've got to be careful. If you think about it, here's 2k, 2k plus 1, 2k minus 1, 2k plus 2, 2k minus 2. We know there can't be any probability at 2k minus 1 and 2k minus 2. I mean, so at 2k minus 1 and 2k plus 1. So what I really should be doing is I should be associating the probability at 2k with what's going on in a window going 1 unit to the left, 1 unit to the right. So what I should really do is I should double the probability of the normal to reflect the fact that I have no probabilities at the odds. Okay? That's one. And then the next thing I need to notice is the following. So what I really should do is e to the negative k squared over n is e to the negative 2k squared over 4n, which is e to the negative 2k squared over 2 times 2n. Why the hell am I doing this? Well, we're looking at the probability that S2n equals 2k, not k. And so when I have it as k squared over n, I really want to have it as a function of 2k, not as a function of k. So that's the first trick. The second one is 1 over square root of pi n would be 1 over the square root of 2 pi times 2n divided by 4, which is 2 over the square root of 2 pi times 2n. And so when I put all of this together, I get the probability that S2n equals 2k is 2 over the square root of 2 pi times 2n e to the negative 2k squared over 2 times 2n. And there's the Gaussian. And everything matches and everything is good. Right? So this is a lot of algebra. In some sense, it's almost nicer to have the proof in general, but this actually shows a lot of the key features that are going to emerge when we prove the central limit theorem in general. This idea of trying to approximate our distribution, this idea of using logarithms to deal with products, this idea of using Taylor series, and then most importantly, just some of the games we have to play. Because we don't take on any odd values, we have to be very careful, and essentially we're doubling the probability. So the even probabilities are doubled, the odds are down to 0. Any questions about this? Given the joy we've just experienced, if you want, try to do, say, the probability of a head is 3/4. And you can just imagine how much worse the algebra is going to be. And this says, maybe there's a better way to approach these problems. And this is the power of generating functions. All right, so at the end of the day, we were able to show this. So everything worked, but again, the difficulty is seeing the path to the algebra. And that is the greatest challenge, is how do I see how to go through this? Well, one of the big hints is we knew the expected value, key input is the expected value of S2n was 0. The variance of S2n was 2n. This helped us know what Gaussian it should be converging to, and this guided us in terms of how to rewrite e to the negative k squared over n. And that led us to send e to the negative k squared over n to being e to the negative 2k squared over 2 times 2n. Okay. So the next is generating functions. So you're shifting gears so that we never ever have to do this again. There are some things in your life that you should do once, and once you've done them, that's enough. Sadly, if you're a professor, it doesn't work that way. So a generating function is given a sequence an. We define its generating function to be the sum of an s to the n for all s where the sum converges. So that's the key fact, is that it may not converge for all s. Can anybody give me a value of s where this will converge? Yes. If I haven't told you anything about the ans, the only value of s where you know it will converge is s equals 0, because then in that special case, you just get a0. So clearly, it will always converge if s equals 0. The question is, will it ever converge for other s? What's the largest regime where it converges? Unfortunately, for a lot of things we want to look at in probability, the generating functions will not converge in the neighborhood of 0. And that's going to make the analysis very, very hard. Fortunately, if you take complex analysis, you can look at a close relation to the generating function, which always exists. And it's much better to work with objects that exist than objects that don't exist. So for example, there's one that you've seen. Let's take the simplest choice of ans that I will let you. What do you think that would be? All zeros, but that's too simple. That's why I said that all ones. So let's take an to be all ones. So the generating function of this sequence of all ones of s is just the sum, n goes from 0 to infinity, of 1 times s to the n. Oh, what does that equal? If the absolute value of s is less than 1, it's just the geometric. So it's 1 over 1 minus s. So here's an example of a series we've seen. And it turns out that we can get a lot of information about this from this equality. We've seen how we can regard this as a geometric random variable. We have to weight it a little bit. If s is the probability of either success or failure, depending on which book you look at, you multiply by 1 minus s, it now sums to 1. We can use the method of differentiating identities and deduce the moments. So this is at least something we've seen before. I'm going to go through warp speed on the Fibonacci numbers. So the Fibonacci satisfies the recurrence relation fn plus 1 is fn plus fn minus 1. How many of you have taken differential equations? Okay. If you were to take differential equations, you would see, this is the subjunctive, you would see series solutions where you have a differential equation, you guess a series, and then you end up getting certain relations among the coefficients. And so I will define the Fibonacci's where f1 equals f2 equals 1. We're going to prove Benet's formula that the n Fibonacci number is 1 over root 5 golden mean to the n minus negative 1 plus root 5 over 2 to the n. And here's how it works. Let's define g of x to be the sum n greater than 0 of fn x to the n. I could start the sum if I want at 0, but basically I'm also using f0 equals 0. So I'm using 0, 1, 1, 2, 3, 5. Each number is the sum of the previous two. At first, this should seem like a foolish thing to do. If we don't really know the Fibonacci numbers, how can we form this function g? But we do know the Fibonacci numbers. Once I tell you the recurrence relation, and I tell you two values, every other value is determined. It's just a question of how can you extract what you know from this. Well, if I sum from n greater than or equal to 2 of fn plus 1 xn plus 1, I use the Fibonacci relation, that's fn plus fn minus 1. And then I can just re-index this as n goes from 2 to infinity of fn plus 2 n plus 1 xn plus 1. That's the same as just writing it as fn xn starting at 3. For the next one, I have fn x to the n plus 1. I pull out an x, and then I just have fn x to the n. For the next one, I re-index, I have fn minus 1 xn plus 1. I re-index, so it becomes fn xn plus 2. I pull out 2 x's, and I have x squared. And what you can see is each of these almost looks like the function g. This is just missing the first 2 terms. The second one is missing the first term. The last one is just g. So what we do is we just add and subtract. We add a net of 0. And so now the first one becomes g of x minus f1 of x minus f2x squared equals x times g of x minus f1 of x plus x squared times g of x. We can now solve for g of x. And we get g of x as x divided by 1 minus x squared. You might think that we could now expand this by using the geometric series and let the ratio be x plus x squared. It turns out that's a horrible thing to do, because if you do that, when you expand it out, x and x squared have different powers. So when you expand, you get things of very different powers, and it's a nightmare to figure out what comes together. Of all of your techniques of integration, which is the technique you hate the most? And pray is not going to be on an exam. Yeah, but there's a specific one that you truly hate. And you might hate it so much, you've actually blocked it from your memory. The least favorite technique. Partial fractions. Yeah, I can say, oh, yeah, I can hear the groaning. Oh, God, yes. Right? Partial fractions. Partial fractions are actually useful. What we do is we write 1 over 1 minus x squared. We factor the denominator. And then when we use that, now we can expand these denominators nicely, because this is now a pure geometric series. And when you expand it, that's where Benet's formula comes from. So again, this is meant to just be a really fast, introduction to some of the powers of geometric series. We started off with the Fibonacci relation, built a function, and it seems strange that we can do this. But because we have a closed form expression for it, we can then use that to deduce information about the local pieces. And now we can jump to any Fibonacci number. So this is a truly, truly remarkable result. Okay. So let's apply it to Poisson random variables. So Poisson random variable, it's our new good friend with parameter lambda, is just lambda to the n e to the minus lambda over n factorial. So let's let this be our an. And then g of a is just the sum, n goes from 0 to infinity, of an s to the n. So we now need to see, can we actually evaluate this? All right, so ga of s is just going to be the sum, n goes from 0 to infinity of lambda to the n, e to the minus lambda over n factorial times s to the n. So what should you combine in this expression? When you look at this, some of the pieces want to get together. Yeah, the s to the n and the lambda to the n. Anybody ever see the movie Ghostbusters? The keymaster and the gatekeeper, we must get these two together, right? I'll pull out the e to the minus lambda. We then have lambda s to the n over n factorial, and goes from 0 to infinity. What does that equal? That's just the exponential of e to the lambda s. So this is just going to be e to the lambda of s minus 1, or e to the negative lambda 1 minus s, depending on how you want to do this. For what s does this make sense? When you look at the sum of lambda s to the n over n factorial, that's actually going to be valid for all s.
Yeah.
So it's valid for all s. Now, let's let xk be Poisson with parameter lambda k. So g of x1 of s would be e to the lambda 1 of s minus 1. G of x2 of s would be e to the lambda 2 of s minus 1. Right? If we let x be x1 plus x2, what's the sum of two Poissons? Poisson, and what's its parameter? Be added, so it'll just be lambda 1 plus lambda 2. So g of x of s would be e to the lambda 1 plus lambda 2 of s minus 1, which is e to the lambda 1 s minus 1 plus lambda 2 of s minus 1, which is g x1 of s, g x2 of s. So I love to convert things to English. The log of a product is the sum of the logs. The derivative of a sum is the sum of the derivatives. How would you convert this to text? The generating function of but what is x? X is a random variable. It's a special random variable. The generating function of a sum of independent random variables is the product of the generating functions. Did we prove that? Hell no. Right? But we at least have some evidence that this might be true. You know, we looked at a Poisson random variable. Now again, Poisson is a very special random variable, but it does look like the generating function of a sum of independent random variables might be the product of the generating function. And so it turns out that that actually is the case. So if you have two generating functions, A and B, and you look at the convolution of the sequences A and B, then the generating function of the convolution is the product of the generating functions. And if you think about it, when we define convolution, why did we define convolution? Because we were trying to calculate the probability of a sum of random variables. So these ideas are all connected. And the idea is that we can hopefully use this to figure things out. We are going to try to prove the central limit theorem. The central limit theorem concerns a sum of independent, identically distributed random variables. That means we're going to have this big n-fold convolution. Oh dear God! You know, remember when we looked at the sums of four normals and we had that terrible formula from Mathematica, and Mathematica didn't even want to try to do the 8 and said, no, thank you. If we now have to do 10 to the 20, really, there's no way we're going to write that down in closed form. But if we have a convolution of 10 to the 20 elements, the generating function of the convolution is going to just be the product of the generating functions. If they're all identically distributed, it's the same generating function raised to the 10 to the 20th power. So we only have to understand something raised to a huge power. What should we use if we have something raised to a huge power? We have something raised to a huge power. Logs, right? Whenever you see powers, whenever you see products, it is a logarithm. When in doubt, say logarithm or Yankee stock, one of those two will almost surely be the right answer. Okay? So all that turns out is that the generating function is not the most useful thing to look at. The moment generating function is a close cousin. It's a little bit better to look at, but it doesn't always exist. So we look at what's called the characteristic function, which always exists. All right, so this is a good place to stop. Have a good weekend. Beat Amherst if you're able to. I mean, we're going to be able to. This is just for the people who are actually playing against Amherst.